We'll resume our discussion with linear regression, the need for regularization, the need for adding so our motivation was basically why did we have this ridge error, it's called ridge regression error, where we had this lambda times 2 norm w square. We started with this inquiry, we did some empirical investigation, and then we moved on to probabilistic interpretation of linear regression. Where we modeled y as a linear combination of w, that is phi x or general x, w transpose phi x, and a stochastic error epsilon, where epsilon was mean zero variance sigma square, which meant that y followed a normal distribution with mean w transpose phi x and variance sigma square. This is where we were, and towards the end of last class we were trying to show also the equivalence between this interpretation, the likelihood association, the maximum likelihood estimation associated with this model, and the least square. Okay. And what is our notion of maximum likelihood? So W star maximum likelihood estimate is one that maximizes with respect to W under the IID assumption the joint distribution of independent identically distributed m errors whereas W star map is minimizer of the ridge error, the least square error. It was a least square error, this was a ridge error. So our goal was to try and show the equivalence of this form and this form. Okay, so what is maximum likelihood estimation? Given IID observations y1 to im generated according to a probability model parameterized by theta, what is P of y given theta? That is the joint likelihood. Okay, so this probability of y given theta is the joint distribution, but when you view this as a function of theta, it is called the likelihood function. Theta given y or theta given the data more generally. So the maximum likelihood estimate theta MLE is in general the argmax over theta of this likelihood function. Now instead of the likelihood, we often optimize the strictly monotonically increasing function, try and maximize that. Would this affect the estimated parameters? And what is the answer? No, and that is exactly what we discussed in the lab tut 1 problem 4. And why apply this log transformation? Why do you do that? Simplify math. So what is the log likelihood? L theta is nothing but summation over the examples, and this is because of the IID assumption. Summation is because of the IID assumption, summation of log of P of y given theta. Okay, so this was recap, and then we also employed this for a simple problem, n coin tosses. Each coin toss is a binary random variable. So basically this is called a Bernoulli distribution. Probability of P of yj equals 1 becomes theta, probability of yj being 0 is 1 minus theta. Well, when I say 1 is synonymous with heads and 0 is also synonymous with tails. Okay, and we saw that the log likelihood estimate turns out to be very intuitive. What is the intuition? Just count the fraction of times you get heads, and that should give you the theta MLE, right? And it turns out that that is indeed the estimate. Okay, and we showed it using log transformation of exactly the this joint distribution that decomposes over the examples. Okay, summation over j yj log theta plus 1 minus yj log 1 minus theta. Summation applies to this whole term, and when you set the log likelihood derivative with respect to theta to 0 and solve, you get this intuitive answer where you are dealing with n coin tosses and yj is 1 exactly when there is heads. Okay, so this matches intuition. Okay, and now we want to quickly verify that all this falls in line with what we set out to show, that this is MLE, I don't know why I wrote map, this is MLE. Okay, we set out to show that W star MLE is the same as W star V squares is the same as W star MLE for linear regression. Let us try and close the loop. For coin tossing it is intuitive, might not be on first sight in the case of probabilistic regression, but it turns out that all you need to do is take the log pass the log through the sum product into and let this transform into a summation, and then they basically log takes over the exponent, right? That's what happens. Okay, so coming back to MLE for linear regression, I've expanded the specific form. The other thing you want to note is also that here we have an argmax. You're trying to maximize. You want that point which maximizes, whereas in the case of these squares there was an argmin. How do you go from max to min? Okay. So this we can. This is obvious. Inside the root. But log likelihood is going to ease our life. Okay, so we move on to log likelihood, the same expression. So let's actually get down, and what we are trying to show is that this will coincide with this minimization problem. This maximization of log likelihood is the same as minimization of this least square object. Okay, let's do this quickly. So when you take log, this part basically will become log of some constant, right? Sigma square is not going to bother us because sigma square is when it appears as an additional operation, summation operation. So summation operation. Why? Because we are dealing with maximization, and when you deal with maximization of summations, summation with a constant can be basically ignored as far as the argmax is concerned. So let's write that. We'll realize that. So this will be m times log So far you are with me? So if I do an argmax, then what happens? So let's say I do so WMLE will be an argmax of this entire summation. Does the first component have anything to do with W? So this can be ignored. Why? Because it's a constant with respect to W. So what you are trying to minimize over matters. If you were to minimize over the sigma, then you can't just ignore this. Now amongst what remains, you just have this 2 sigma square in the denominator. it comes out common across all the summands, right, all that you are summing over. So again in some sense you can ignore this. So you have exactly minus of summation yj minus w transpose xj whole square, and you are trying to maximize. So if you flip the sign and do minimization, will you get the same answer? Okay, so make two changes. Make this argmax over w with as argmin over w, and flip the sign there. That's it. Okay, so all you need to realize is theta, which is obtained as argmax theta star, argmax over theta of f theta or minus of f theta is the same as argmin over theta of f theta. Is okay? That's it. So we have basically proved the equivalence. Any questions? We have proved the equivalence between the least square estimate and the MLE estimate for specifically for linear regression. This is under some assumptions on the form, that the form of the distribution on epsilon, which we sufficiently motivated. What was the motivation for this? One was noise. We would expect the expected value of epsilon to be 0. Gaussian distribution is the distribution with the highest entropy given a specified amount of variance. There is also another reason which I didn't mention last time. If you look at the form of the Gaussian distribution, you will find that 99.9% of the points lie within 3 sigma band around the mean. So the points are not too spread out. Okay, so reasonable assumption, under reasonable assumptions we get this equivalence. So error is not all over the place. The error component is somewhat controlled. I am not saying that's the main motivation, that's also an observation which also makes sense, that errors are not spread out all over. I mean we are interested in modeling errors which are somewhat controlled. Error is supposed to be a small perturbation around the actual observation and are not supposed to overwhelm and take over the actual observation. Okay, so given this form in your lab as well as in the previous classes, we talked about analytically finding solution, right, in closed form solution. We found the least square, and now we know it's also the MLE estimate, which is phi transpose phi whole inverse phi transpose y. However, it turns out that for several reasons you might also want to consider iterative methods, algorithms that progressively search. Okay, so search algorithm that progressively decreases the error function. What these algorithms do, so let us say I have a two dimensional view of the error function, let us say just W1 and W2, and these are the level curves of the error function. What are level curves? So this corresponds to the one outside. Let me use different colors. So level curves U, where let us say the red corresponds to all the W1 comma W2 values for which the error value EW1 comma W2 is constant, and it's a red constant, okay, constant 1. On the other hand, the ones in green, the curve in green is all W1 comma W2 such that the error value observed around for those set of points is another green constant. Okay, I can plot multiple such curves. Now it turns out that locally, if you compute, if you are able to compute some direction such that you move from a region of, let us say, higher level curve, let us say we are talking about errors, right, which means we want to reduce, you move from a region of higher level curve to a lower level curve, then an algorithm like this which keeps refining its direction, always locally refining it based on level curves that have lower energy. So think of error also as energy, you want to minimize the energy, right, and you know that at the subatomic level all particles try and minimize, I mean you want to reach a configuration where there is minimum energy. So a lot of this discussion also comes from particle physics. So let us say const 1 was less than const 2, so we want to be able to go from, we want a direction that is suggested which will be in the direction from green to the red when I am situated on red, and then when I go back to, when I am back in red, I might have another direction, it might get further refined. Okay, so the direction vectors are in the W1 W2 space. Okay, so this is the idea behind most iterative algorithms. The visualization of these algorithms is also best done in the space of these level curves. So can you think of a vector, the vector in grey, which keeps to be refined based on where you are in the level curve? Can you think of some vector that will correspond to the vector in grey? Normal, right, and did I talk about one such normal vector? Gradient, right, I mentioned that gradient is the direction of descent, well in a Euclidean space. I mean I am showing all this in Euclidean space, you can change the space and things will geometry and also the notion of the steepest descent direction will change, but Euclidean is very easy to relate to. So in the Euclidean space, the direction of steepest descent for a differentiable function turns out to be the gradient vector. Okay. So the new value of W that is being referred to gradient EW. We are now discussing the need for EW. So we are talking about descent is negative of gradient. Gradient is direction of increase. I mentioned descent here, so gradient is the direction of maximum increase. Negative of gradient is the direction of maximum decrease. Okay. So gradient descent is an iterative algorithm to find the minimum of a function. Specifically, this is how you would write the iteration. So you would say let's say W is this Wk plus 1 is the W vector estimate at the k plus 1th iteration. That would be given as Wk minus some eta times the gradient vector at Wk. Now what is this eta? So when I make a descent, I want to know how much should I descend. The direction is a negative of gradient, but the magnitude is something you need to figure out. Again, that's something you are dealing with in your lab assignment 1. Some of you complained that the error values are turning out to be very large, right? So possibly you should play around with the step size. This is eta is called the step size. Any question? I was discussing more in terms of the level curves and the local moves that any configuration takes. So yeah, so these inspired algorithms are inspired, obviously. You will find this deja vu feeling, the same thing kind of reappearing in many other domains as well. Okay, so this is the basic idea. Now specifically in terms of the individual components of W, you can write as Wi is updated as Wi minus eta times the partial derivative of E with respect to Wi, right. So I'm explicitly using Wk as W vector at kth step / iteration. This is superscript, and Wi subscript is ith component of W vector. So here I have not invoked the iteration notation, but you can also put a k plus 1 here if you want. You can say Wi ith component at k plus 1 iteration would be Wi at kth iteration minus eta minus eta the partial derivative with respect to Wi. Sorry, this is better, best done just by saying evaluated at Wk. This is a better notation. You should ideally not mess around with the partial derivative notation, but evaluate it at a specific point. This is how you done it in, I mean, you have treated these evaluations in your calculus course, I believe. So is eta independent of K? Good question. Need not be. So eta need not be independent of K. In many settings, eta doesn't change too much with K. See, eta may change with the data set, the nature of the loss function and so on, but you don't expect it to change drastically. A small multiplicative factor could be used, so you can dampen it, dampen the value of eta. Let me make that note here. Okay, so these are the two observations. Order of magnitude depends on the nature of the data set. So order of magnitude of eta you won't expect to change across iterations, right, whereas specific value of eta could be somewhat varied across iterations. Now the issue we have with eta, the reason we have to work hard to tune eta is because we are not considering the curvature of the function, right. So suppose these were the level curves. I mean, I could actually be aggressive in eta. Eta could be large. Whereas if I had these curves and if I were somewhere here, right. So if I took a large value of eta, I would probably I would do better by taking small values of eta and kind of revising my direction slightly at every step. And these are still nice curves, but you could have level curves like these, where your eta could actually take you completely off track. So now there are second order methods which look at the nature of curvature, account for the curvature in estimating the direction as well as the step size. In fact, step size is computed indirectly or implicitly along with the direction. So they are called Newton methods, quasi-Newton methods, which try and account for the curvature information. So they decrease the over dependence on eta, though I must point out that these quasi-Newton methods are expensive to compute because they often require you to compute the mixed second order partial derivatives, partial derivative with respect to I and j, right. So they are expensive, computationally expensive. So as all know, there is no free lunch. You pay something, you reap some benefits. Somebody had a question? Okay, that's all we will discuss. I mean, if you are interested in more details on this, you can take a course on optimization, which might be offered next semester or the semester after that. Okay, so yeah, they are the guidelines. If eta is too small, very slow convergence. If eta is too large, may overshoot the minimum. And the reason is as shown on board. One is unaccounted for curvature, and when we say curvature, you could think of it as these second order derivatives which we have not accounted for. Also it could happen that there are multiple, the curve is not very well behaved, it does not have just one local minimum, it is not convex. Okay, so I have shown that on the board in the case of using level curves, but I can do that also in the one dimensional case. Let us say this is my EW and this is my W. So my curve might look like this. So I might very happily be trying to get to this guy, but this is a local minimum. whereas I should be trying and getting to here, right. So this is a local minimum, whereas this might be the global minimum we should have got to. Okay, I mean it's the objective is convex in some regions but not convex everywhere. Okay, these are other reasons. These are reasons for why choice of eta, there's oversensitivity to choice of eta, why eta might play a very vital role. Because if you had this case, right, I mean I won't be super sensitive to your choice of eta. Obviously I don't want to overshoot even here, but then slightly off is okay. We seem to be proceeding in the same direction, have the same curvature everywhere. In fact, gradient descent is motivated by this. This is the basic assumption, because this is the Euclidean kind of Euclidean level curve or level curves under the Euclidean metric. But here you have some matrix based transformation. So have you heard of the Mann-Lobis distance? It's a statistical distance between points based on the covariance structure, right. So something like this would be what the data is talking about. So gradient descent is in this nice dream world. This is a gradient descent world, and this is your real world. Right, and eta is your mediator between real world and gradient descent world. So you can rescale and then have this, yeah, but it's not easy. I mean, what would you do in this case? And what would you do if this was tilted a bit? So this is fine, because yeah, if you had a slight rotation, then what does it mean to just scale W1 or W2? No, there are tricks, but then we'll have to discuss this in another course. But yes, there are tricks. So I'm just giving you a basic idea. As I said, there are quasi-Newton methods which don't directly consider these curvature through second order derivatives, but they find it through some rate of change of the gradient and so on. You can keep computing gradient and how it changes across iterations. But for the purposes of this course, this is what you'll mostly be doing. You'll be tuning etas. Okay, so let's move on and do map estimation. Okay, so map estimation is connected to ridge. You already got exposed to ridge in the last class and also in the lab, but now I'll give you the mathematical underpinnings. Can someone lend me a coin? One is sufficient, and return it. Okay, thanks. Okay, so what we are going to do is look at maximum likelihood versus a posteriori map, which is maximum a posteriori estimation. So I toss this coin, I got a heads, and it was tails. Okay, but let's say I did this 4 times heads, so 3 heads and 4 tails. Pardon? So 3 heads and 4 tails. Now based on this, can I reliably say that the probability of heads is 3/4? is there a difference between me tossing a coin 4 times, getting 3 out of 4 heads, and me tossing the coin say 40 times and getting 30 out of 40 heads? Is there a difference? You want to be able to differentiate, right? Then you are basically prepared for map estimation, because if you believe that doesn't make a difference, right? No many if it's 3/4 of the times that you get hit, doesn't matter how many times you have tossed, then you are not able to kind of factor in that there is a prior belief you had, and the amount of evidence that you are aggregating is shifting your belief system, right? I mean, if every course in IIT the maximum CPI, so let's say the first year maximum CPI maximum grade was say BB, right, and you find that in every course, and second year again you find BB, nobody gives more than BB, B square, and if you find this in the fourth year, you ye to halat hai IIT ki, right? So your beliefs get reinforced. If maybe 1 year you find that, one course you find that you think it's an aberration. So when we do say that something needs to be done with this prof as against with the entire system, it's based on how often you see. Okay, so we want to be able to factor that in. So we are implicitly dealing with prior distribution here. Sorry. Now what you want to kind of make more explicit is that when you observed 40 coin tosses and out of that you observed 30 heads, your prior belief was affected or shaken up a lot more than when you observed 3 out of 4 heads, right? 3 heads out of 4 coin tosses. So again the distinction is the prior belief is more affected. Okay, so let's call this case 1 and case 2. Now how do you model the prior belief? So we will talk about conjugate priors and we will stick to our coin toss example and then go back to linear regression and connect ridge regression with map estimation. The coin tossing is easier, you guys are very kind and lend me coins, but it's difficult to show linear regression estimation in n dimensions. So we will continue with coin tossing, recap the MLE estimation, right? The MLE was again very hard with us. N is 4, summation yi is 3, for us is the same as saying summation yi is 30 and n is 40, doesn't make a difference. So otherwise it's just recapping MLE. So what do? We incorporate prior knowledge. So when I started the tossing of this coin, I kind of had a prior knowledge that this should be fair. So head and tails are equally likely outcomes, and let's say I have all heads. Now that may be an extreme case. Now if I have prior that it is fair and I see all of them heads, this is a case where maximum likelihood estimate will be what? 1. but I want my theta map. What would I like theta map to be? Would you like it to be 0.5 still? Doesn't make sense. I mean, इतना सब देखने के बाद 0.5, right? Dull है बंदा. So what do you say? Okay. So you would say, well, this should be somewhere between certainly greater than 0.5, but certainly less than 1. This is what we want, right? Can we arrive at this? Okay, so this requires you to just use probability all through. So let's recall what theta MLE was. Theta MLE was argmax over theta of the probability of the data given theta, right? This is what we call the likelihood function. This probability of data given theta is exactly what we refer to as the likelihood of theta or the likelihood of theta given data. This is what we used. What theta map will do is slightly different. It will say, well, I want to maximize with respect to some objective, but I will try and maximize the probability of theta given the data. Now suddenly you are referring to theta as having a distribution. What does it mean to say probability of theta given data? I mean, so far putting theta in conditioning was basically it's like semicolon theta, like theta is a parameter, right? So here theta was a parameter. So instead of I mean, it's better to just do the following. Instead of saying probability of theta given data, I am just going to write it as, so probability of data subscript theta, which I was also referring to as this, I was referring to as likelihood of function of theta, but subscript d. So as I said, subscript d, I was using it in the sense that this is a distribution pivoted on d, so the distribution for d pivoted on theta. But here we are actually talking about a distribution, right? And if I were allowed to use the base rule, which I should be allowed to if I am talking about a distribution. What's the base rule here? BAYES, base rule, base theorem. What can I, this should be the same as P theta given D, okay, so I'll use it step by step. P theta comma D divided by P of D, and I can further expand. So I should be able to talk of the following. I'll further expand the numerator. P of D given theta into P of theta. I should be able to talk about this. P of D given theta into P of theta divided by P of D. Okay. So I am going to write this more clearly here. Now if I do an argmax, does P of D matter? P of D, the data is already given when I am doing an argmax over theta, right? So I have just expanded this here. So I am going to clean up the right hand side and say this is nothing but argmax over theta of P of D given theta into P of theta. So P of D is a scale factor independent of theta. Is this clear? So I need a P of theta. So the fact that coin is fair is going to reflect in P of theta the choice of distribution that reflects a fair coin. That is my prior belief. My prior belief will be in the form of a probability distribution on theta. Theta is no longer only a parameter, right? Theta, well, it is a parameter for the likelihood, I mean for the probability of the data, but itself has a distribution. Theta is now a belief system. Okay. So again, just to complete this point in words, for this 5 head case, theta MLE is 1, is not intuitive. This makes the tails improbable. Is there a way we could update our belief about the coin? We also want to be able to update our belief about the coin, right? And that is the other reason why we will also be interested in P of theta given data versus P of theta. What can you help me express in words what each of these two mean? What is P of theta and what is P of theta given data? Probability that coin is fair. Yeah, but fair is one form of distribution, I mean, or one artifact of the form of distribution you choose, right? But I mean, I could say it's 0.6. I believe that the mean is 0.6 or whatever, right? So write it more generally, not in terms of fairness alone. So P of theta is my prior belief, right? It's my prior belief before I observed any data. P of theta given data is my posterior after I observed data, my posterior belief distribution. And belief is in the form of a distribution. P of theta given D is the posterior belief after data was observed. Okay. Now so far so good, but now I want to get into more specifics. Okay, and I keep this on the board because I want to remind you we are trying to deal with this, we are trying to get to this modification somewhere, somehow or the other, and they are connected. Okay, so let's do the coin tossing case again, keep that in mind. So what I know, what I have is P theta is my prior, P of theta given D is posterior, P of D given theta is a likelihood. In the coin tossing case, what is the form of the likelihood? Let us say n coin tosses I have, n or m, let us say. Okay. So then theta raised to yi yj 1 minus theta raised to 1 minus yj. This is my likelihood function. We will stay with this. Now I want a form of the prior and the posterior. What would you ideally desire? Prior to be half, understand. See, but the point is we are dealing with distributions. Half is an artifact of that choice of prior. So don't keep thinking about fairness. Fairness is one instance. I mean, I can have a prior which says no, most of the times it should be head. Why always a fair prior, right? So think more in terms of distributions. What would I like these forms for mathematical convenience? See, we also want to be mathematically have simple forms to deal with, yet at the same time it should not go completely against intuition. So can I say that the form of the distribution p theta and the form of the distribution p theta given d should be similar? I mean, would you be happy if p theta looks like a Gaussian and p of theta given data looks like some other distribution altogether? The parameters could be different, but wouldn't you like that they have a similar form? Yes or no? Again, it's mathematical convenience, I would say, but to some extent it's also intuition. So you do whatever you want, but give me a similar form. And now I would bring back Bayes' rule. So I will say that P of theta given d I know is proportional to P of d given theta into P of theta. We saw that already. Just divide by probability of data. That's like the probability of data doesn't depend on the theta, right? I mean, so probability of data, that's it. This is important. I know the form here of the probability of the likelihood function, and I want probability of d given theta and probability of theta to have similar forms. Okay. So the form of p theta under this proportionality assumption, given the likelihood, the Bernoulli case, right, Bernoulli likelihood, that form which gives you this desired characteristic that the form prior and posterior have similar form is called a conjugate form, conjugate to Bernoulli. Okay. So when we say this similar form, we require it to be conjugate to Bernoulli, because this is the Bernoulli likelihood. Okay. So the Bayesian way is treat the parameters as random coming from a distribution, impose a prior distribution of parameters which indicates one's previous belief. Okay, this prior distribution p theta, and when you multiply this p of data given theta, okay, I mean you get p of theta given data which is proportional to this product. And this is the posterior. So what is happening here is the posterior updates our prior belief about theta in the light of the observed data. And the point I made so far is this belief, if the belief distribution is conjugate to probability of data given theta, then probability of theta given data and probability of theta have similar forms. Okay, and I will now quickly come to the main point, how this is possible. Same point which I mentioned on the board, I am highlighting it here. So this is the whole idea of maximum a posteriori estimate. So I will take a very simple example. Let us say my probability of theta, in my prior, say theta could only be either 0.1 or 0.9, only two values. I can possible, right? And probability of theta equals 0.1, let us say is 0.1, probability of theta equals 0.9 is 0.9, no other theta is possible. So let's do the simple problem, solve the simple problem. And now let us say, as before, we observe 5 heads out of 5 tosses, right, in which case theta MLE is 1. Now what would be theta map? Let us take the simple example. What would be theta map? So I am telling you that, well, I am giving only two specific values, nothing else is possible. So theta map will be either 0.1 or 0.9. Either only two values are possible for theta. Now which of the two seems to be more likely to produce 5 heads? 0.9, right? So common sense says 0.9, verify it, quickly verify. Quickly verify that this series of expressions gives you exactly 0.9. As per common sense, theta map is 0.9. So you need to just compute these probabilities. Did you get the question? Anyone is unclear about the question, please let me know. Theta is exactly only two values as per the prior. No other values are possible as per the prior. So this coin, either theta is 0.1 or 0.9. My prior says theta is 0.1 with probability 0.1. Exactly 5 heads out of 5 coin tosses. So you can compute. Probability that theta is 0.1 given the data, that is what will give you the map, right, is proportional to 0.1 raised to 5 into 0.1, which is the probability of 0.1, right. Probability of theta is 0.9 given the data is proportional to 0.9 raised to 5 into 0.9. इनमें से बड़ा कौन है? As simple as that. Okay, but now it's a very too simple a prior. I mean, priors cannot be like this, right? The OE values 0.1 or 0.9. I mean, और क्या है? I mean, that doesn't. It sounds too too good to be. I mean, and why only two values? So we want to be able to now, as I said, we want to have a conjugate prior. We will have a conjugate prior to this Bernoulli likelihood, and that is called the beta distribution. Okay. So the idea will be as follows. If you do a theta map now, which is argmax over theta of probability of data given theta into probability of theta. It will be an argmax over a beta distribution again. And what is this beta distribution? Okay, so now this is a fantastic beta distribution. Beta will have two parameters, alpha, beta, and let's say I have observed k out of n heads, right? So what will happen is, this was beta before observed anything. After I observe the data, which is k out of n heads, I will have this mathematical convenience which gives me beta of alpha plus k and n beta plus n minus k. So tell me what you observe. So what is this plus k? Number of heads, number of tails. So this beta distribution is some fantastic distribution where I fold in k out of n heads, and after the posterior just say, okay, originally it was alpha and beta, now it will become alpha plus k and beta plus n minus k. The form of the distribution I will quickly show, that is not so important. The important point is this conjugacy. This is assuming the Bernoulli distribution. Now what is the function of alpha and beta here? What are the functions that they are serving? If you want to call them A and B instead of alpha beta. What purpose are they serving? Our prior belief, how many heads and how many tails. Alpha is serving the purpose of heads and beta is serving the purpose of tails, which makes sense. After my observations, I am just updating my alpha and beta. Okay. So this form, this is called the beta distribution. Now it has this form. And as I pointed out earlier, this alpha it's called a hyperparameter. Number of heads. So imagine I had a long sleep and in my dream I saw the coin being tossed some number of times, and that is my prior. My prior is coming from my dream. Alpha heads. In my prior, and then beta is also hyperparameter and it is a number of tails in my prior. Now does this make more sense than just saying 0.1 and 0.9? Because 0.1 and 0.9 were just two points, but here now I am giving possibilities, right? So there's a possibility of 0.8, 0.6, 0.5. This is richer than just saying P of theta equals 0.1 is 0.1, P of theta equals 0.9 equals 0.9. All theta values in 0, 1 have non-zero prior. Now one last question. Fairness. How can I bring in fairness here? When will this distribution looks exactly alpha equals beta equals 1? What will happen if alpha equals beta equals 1? This will become a uniform distribution. Is that what you wanted? No. So if any alpha equals beta, the larger the value of alpha and beta, the more you are insistent upon fairness. So alpha equals beta means fairness. But how strong are you with fair? Nah, fair hai. Nahin, fair hai. No, there's a difference in the tone, right? When I am very assertive about it, very large values of alpha and beta. And chalta hai. Thode hawa ke jhoke mein I can just change my belief. Then alpha and beta are probably 1, right? So alpha equals beta equals 1 implies fair coin. Larger alpha equals beta implies greater belief in fairness. Okay.